their MS work. For the most about him and what will stand out for years to come is the number of obstacles that he overcame to complete his MS work. So Jakob, he originally was interested in being in our research group, and he would email me a number of times saying, "Oh," he said, "okay, do I have funding? Can I be an RA?" And then finally, you know, I hem and hawed, and then finally I said, "Oh, okay." And so then he came and they found out that, oh, wow, he was really good. He was a very hard worker and very diligent and could work independently. And so he did some work with Robbie on Kiasun, working with Robbie and Jason that he really won't talk about here, but did a lot of useful work on the reporting of our Kiasun verification tool. And so Jakob could do so much on his own and independently that I said, okay, there's a really hard problem I don't know how to solve. So it's very dangerous as a problem to give to a student when you don't know how to solve it yourself. But I said, Jakob, there's an interesting thing that you might do, and that is actually program or build a mini prototype of a PCA pump and actually use some new technology that we're working on that some of our industrial collaborators are working on. And so Jakob, he was like, okay, wasn't smart enough at that time to realize what a trap he was walking into, but he said, okay, and then he proceeded for about at least close to six months almost to the little board that he'll give a demo over there on the computer board, not the whiteboard. He will give a demo on, he worked with that and engineers at Adacor to get this new technology, Spark, working on that. And then he was faced with some other challenges, getting other tools that were really research-oriented tools coming out from other research groups working. And so he had a very ambitious project, and he's able to sort of give a vision in his work of what might be several years down the road by exploring various pieces of the puzzle, whether it's the implementation on the board, give a vision of what some of the verification technology might look like, what various model-driven development technology might look like. And so I'm going to hand it off to Jakob to explain how he's done some groundbreaking work in each of these little areas. And when I talked to him yesterday, he said, oh, I practiced my talk and it went an hour and a half. And I told him, especially after Robbie insisted that, no, we need to keep it 30 to 45 minutes. And so I have already taken up 5 minutes of that. So you have 5 minutes less than we agreed yesterday, because I've just taken 5 minutes. No, whatever. Just go and try to get us.
According to my blog, I have it's 2:01.
3:01. Okay. Oh, good. So I started early.
You're not trustworthy. You have a vested interest in this.
Okay. Great.
All right. I'll try to keep it short. Yeah. So my name is Jakub Indryszek. I am research assistant in Santos lab, and last year, because last summer I started working on my master thesis research. I was working to create a PCA beam fusion pump prototype. And I was proceeding model-driven development because I was developing it based on already existing models, and the goal of it was to propose the automatic translation from the models to the existing code. And now I'll tell why I was doing that and how I did it. So currently, medical devices works rather independently. And that's a problem, because if we can connect different medical devices, work in a network and communicate between each other, we can avoid some issues which we have. And there is this idea of integrated clinical environment, which will create a network of medical devices. And medical device coordination framework is implementation of ICE created by our research group, Santos Lab. And the PCA pump is some example medical device which ultimately work under the medical device coordination framework. And there are two techniques which are important for safety critical systems. And medical devices are safety critical systems. We don't want them to simply break or get Stack Overflow exceptions. So in order to avoid any issues, we do software verification. And the difference between software verification and software testing is that in software testing, we test some particular scenarios. For example, let's test this infusion pump, whether it can work for 10 minutes in this basal rate. But in software verification, we are testing all possible scenarios, and then we can, for example, discover that, oh yeah, if you run this pump with this flow rate, then after 37 minutes, there will be some operation which will cause division by 0, and the system will basically broke, and then it might cause overinfusion and some other issues. And model-driven development is another technique which is useful in also software verification, because we can start verifying our device in an early stage of design, when we can have higher level of abstraction, so we don't need to focus on implementation details, but we only look at the high level and all possible issues, or we can make some design decisions. And the PCA pump is a medical device which is used for a patient, usually after a surgery, to deliver a painkiller. And what is sort of unique about this device that it allows patient to control the dose of the painkiller. So the pump works in sort of 5 modes. Stop mode means it's of course off, and the basal rate is the continuous dose which is delivered to the patient, programmed by clinician. And then when patient feel pain or uncomfortable, he can order additional painkillers by pushing the button, which we can see here. And the patient is usually allowed only to request this additional boluses a few times. It cannot, requesting boluses like all the time to get as much drug as he wants, because there is some safe limit. But in some extreme scenarios, clinician can order a clinician bolus, which will allow to add another dose, because sometimes human body is very different for every human. So when a clinician see the patient, he can say, okay, it will be safe to add a little bit more, and we can do that. And there is also the keep vein open mode. In this mode, pumps switch in case of underinfusion. Pump is not shut down to stop mode, because we want to keep the vein open. Because if we stop it, then it will cause the vein to close, and then when we restart the pump, it can cause issues with the vein. And the keep vein open is usually very small, right? Like 1 milliliter per hour. So it's almost nothing, but it's something in order to maintain this vein open. And this is how a PCA pump looks like. Here is the vial with the drug. Here is the panel for a clinician to program it. And here is a button for a patient to request the bolus. This is modern version of pump created by Alaris company. And here is the vial. Here is the more rich patient button. And here is, of course, the clinician panel. So what is surprising, that currently the medical devices already are network enabled. They have Ethernet ports or even Wi-Fi, but usually it's used for example, to communicate with some monitoring device to display the data from the device on the monitor. What we want to propose and integrated clinician environment is to create a centralized system which will advise all different medical devices. And for example, in the case of PCA pump, there were accidents when a patient got a too high dose. For example, there was one particular accident when the nurse took higher concentration of drug, and then the patient got this drug, and the pulse rate was going down and down. And when the clinician came to the patient room, it was too late to save the patient life, and the patient died. So, and the solution for that, in case of ICE, is to have this system which will have data from pulse oximeter, which will deliver data about the patient pulse. And if the pulse will be too low, it can issue an alarm, and then the centralized system will order PCA pump shutdown, which will stop delivery, and it can save patient's life. Additionally, the system should be connected to drugs database, or in the ultimate scenario, the clinician should have tablets like Microsoft Surface to go from the room and monitor all different patients, and then advising will be much better. A medical device coordination framework idea is sort of implementation of this ICE, as I mentioned, and there are devices which can be connected. One of these devices will be PCA pump, and what is important here that there won't be probably single company which will make those devices. So in order to allow different companies to make devices, there will be a set of requirements, and based on these requirements, the devices will be created, and then through universal interface can interact with MDCF. So the summary of goals for my research was first to create the PCA pump prototype, and the foundation for this work was system requirements created by Brian Larson. And in addition to these requirements, there was hardware and software models of the pump, and based on that, I need to propose translation. The models are in AADL language, and translation, and the target language was Spark Ada, which I will talk about later. And at the end, I had to perform a verification of this translated or created prototype. So quick overview of technologies I was using. So AADL is a modeling language. BLES is extension to AADL. So AADL along with BLES is the model of the device. And as a programming language, I use Spark Ada. So for those not familiar with AADL, this is sort of UML for hardware and software, because in UML we just model the software parts, but in AADL you can model hardware and software together. And it has nice textual representation and also graphical. And here you can see a simple thermometer, which actually have two devices, display and the actual thermometer, and they communicate through input-output ports. BLES is a language created by Brian Larson, the author of the requirements for PCA pump and also AADL models. This language allows, in addition to architecture modeled by AADL, it allows to model the behavior of the components. And there are three sort of sections of BLES. First one, which is the main focus in my research, is assertion. So for example, when we have some example thread which works in, for example, some period, then every time the period is going, we check example assertion, whether it's valid or not. And BLES is much richer language, but it's also sort of complicated and hard to translate to Spark Ada. And there are also notion of states and transitions, which is very hard to deal in because of the notion of the time in that. So Ada programming language, which Spark is based on, is object-oriented and statically typed language. It was designed especially for safety-critical systems. And for example, Boeing 777 has 99% of its software written in Ada. And by the way, Ada is named by the first official computer programmer, Ada Lovelace, who created the algorithm which should work on Charles Babbage analytical engine, but it was never built, so we don't know whether it worked, but this is considered as first computer program. Spark is a subset of Ada for software verification. I would say it's sort of like a research subset, because Ada is pretty rich language and it's hard to perform software verification on it. So the researchers decide, okay, let's make some subset of this language. Let's get rid of, for example, recursion or exceptions, and then we can easier reason about the program correctness. And then with new versions of Spark, the Spark has a richer subset of Ada. For example, until Spark 2005, which was subset of Ada, and in addition to that, there was code contracts. Like here on the left-hand side, there are pre and post conditions, which were encoded in Ada comments, because comment in Ada is 2 dashes, and if you add # after that, then there is Spark contract, and Spark tools can detect that it should analyze this. And now in next version of Ada, 2012, they get this idea of code contracts from Spark 2005, and now the contracts are part of the language. And also, like in next version of Spark, for example, now recursion is allowed. So the progress has been made. Of course, concurrency is also an issue for software verification. And in Spark 2005, it is enabled by Ravenscar profile. More precisely, the Ravenscar profile is it's like a set of restrictions for Ada programs for safety-critical systems. And Ravenspark is a subset of Ravenscar, which only have Spark language features, doesn't contain the Ada features. And it allows to use Spark verification tools to verify even concurrent programs now. And the features used by me is most those 3 things: tasks, protected types, which allows for safety sharing variables, and time library, because I need to measure a time. For example, I need to run the pump for 5 minutes, and then I need to have this notion of time there. The verification in Spark is based on discovery of possible states, and this discovery is based on generating verification conditions, and each verification condition check for such a things as array index out of range, division by 0, type range violation, and other things. And there is also dead path conjectures, which check all the path generated by, all the possible path generated by the tool. And for example, when we have if-else instruction, we have 2 paths in the program. One goes through the if, another through else. But if the condition of if is 1 = 1, then we'll never go to the else, because we always go to the if. So then we have that path in the else statement. And the tools can indicate this. And the Spark 2005 tools, the most important tool is Examiner, which generates verification conditions and dead path conjectures and discharge them. But it might be possible that some verification conditions are not discharged. Then we can use Simplifier, which simplifies the verification condition and tries to discharge them. And ZombieScope do the same, but for dead path. And if this failed, there is a tool called Victor, which converts the generated intermediate representation of verification condition and dead path, and it converts it to format for SMT solvers. SMT solver is a tool for solve mathematical theorems. And at the end, there is a tool, POX, Proof Obligation Summarizer, which analyzes all these files generated by verification tools and create a human-readable form and sort of report.
So what does Examiner use for discharging?
Examiner is used to generate the verification condition and that path and to discharge them.
So does it use some other tool as a subroutine to discharge the conditions, or like SMT solvers, or does it have?
No. First you run Examiner, right? And then you have some verifications proof, some not. Then you run. Then if some are not discharged, then you run Simplifier. So it can discharge.
So Examiner has the logic to discharge it as well?
Yes.
Okay.
Yes.
That's one.
All right. So Bakar Kiesan, this is a tool created by Dr. Robbie and Jason, and it uses symbolic execution for also discovering the states, and it has nicer user interface because it can generate counterexamples. For example, because sometimes indication, oh yeah, here you can have overflow. Okay, but when program is complicated, okay, how I can have this overflow? And then Bakar-Kiesan gives you like example and can say, oh yeah, this number will call this, will cause this. And there's also unit test framework called AUnit, which works like JUnit for Java or AUnit for .NET. And in Spark 2014, there's new tool called NutProof, which do basically the same things what first four tools for Spark 2005. It has better user interface as well, but it's still under development. And there is also Bakar-Kiesan V2, which is for Spark 2014, which is also under development. The platform for the PCA prototype is BeagleBoard. This is $150 board. Pretty powerful because it has 1 gigahertz processor. There are general purpose input-output ports, which allows to control the actual device. And there's a Linux operating system, so you can use it almost like a PC. And that's why it was chosen as a platform for prototyping only. So the first challenge was to run the Spark ADA program on this BeagleBoard because there was no native NAT compiler, no official NAT cross-compiler, and usually when people are compiling something, they create customized compilers for particular devices. And by the way, cross-compiler is when you, for example, compile something for some platform, but on the other device, other platform. So based on everything I had, there is a research plan I was following. So first step was to compile this Spark ADA program for BeagleBoard, check Spark 2005 and 2014 whether they work. And the next step was to start the implementation to see how how Spark ADA works, what features can be used, and so on and so forth. And simultaneously, because I was based on the models, so simultaneously I was developing the possible translations, how some constructs from IADL should be or can be translated into Spark ADA. I was mainly based on a tool called Ocarina, which is created by other researcher, but this is pretty heavyweight tool because it runs on top of a big framework called PolyOrb. So I was only actually using the higher level mappings proposed there. And at the end, when the translation will be done, I wanted to do verification on the implemented prototype and also in translated, like raw translated models into the code. And to also take advantage of Kiesan, which doesn't support multitasking, I created a small module to use all tools plus Kiesan to show the example verification. So as Dr. Hadquith mentioned, the cross-compiler for BeagleBoard was created in cooperation with Ada Core. They already had cross-compiler, but for Android platform, and was not working, unfortunately, on Linux and on BeagleBoard. So after exchanging like 40 or 50 mails and getting new bundles and versions, finally they delivered the cross-compiler. And I was actually surprised that after that everything was working. Tasking, there was no issues because it was so hard to compile Hello World, but then everything else was working because the issue was the starting code, which was starting the actual program.
So you also support x86 as well?
Well, actually, only one platform on which the compilation can be done is 32-bit Linux.
Oh, the compilation has to be done now.
Yes.
Okay. It's not
Yes.
target.
Yeah, and in the future maybe they will consider other platform, but for now it's only this one. But good enough. So the translation I created during the prototype development, and based on programming language annex document, it's like appendix for AADL standard. I created translation for data types, for ports, for threads, subprograms, feature groups. Feature group is like a set of, for example, ports. Like for example, when we want to have interface to MDCF, then we can define like feature group with input ports and output ports in order to send and receive messages. And then when we have different modules which we need to communicate with MDCF, we are just in the model we just use the feature group. And in Spark Ada, the classes from Java are named as packages, and the same thing is in AADL. And AADL package contains, for example, threads, but also processes and systems, and also can contain subprograms. So this is the also sort of the higher level entity. And property sets is, let's say, class with constants in Java. So property set in AADL is, for example, we have definition of a KVO rate. It is 1 milliliter per hour. We have the definition of drag library size. It's 1,000. And they were translated for Spark Ada packages and represented as a constant. In addition to AADL translation, there is also some work on blessed to Spark translations, mainly on assertions. I will show example later on. And the most challenging was port-based communication, especially how this communication should be realized, especially before between different modules which are independent. And here, what was fortunately not available would be very nice to have consultation with some developers who already create such applications and how they did it, but there's no much resources on Stack Overflow or even on Google. When you Google for Spark Ada, usually, well, you find Chevy Spark, or I was Googling for Spark Ada for medical devices. I found was medical devices Spark FDA evaluation. So actually this is very cool because there's the idea of printing medical devices. So maybe someday the hardware part of ADL will be also taking into account, and we'll be printing the hardware and generating the software, and we'll have automatically medical device. And during the development of translations, the biggest challenge was the Spark limitation, because it's nice for verification because you don't need to worry about a lot of things. But for example, it's really hard to developing programs without such a thing as dynamic allocation, when you cannot just allocate an array or allocate different number of objects and so on. The PCA prototype, which works on this device, is implemented in Spark 2005, because at the time I was working on it, and even now the Spark 2014 is just not ready. There's no tasking in Spark 2014. In Spark 2005 is it available? And what I actually needed to make some working device was to translate the data types and the operational module, the main module of the pump. And I also separated the module responsible for controlling the actual device. So it works in such a way that from the operational module, I request 0.1 milliliter dose, and the PCA engine module is doing this. So for example, I don't set the speed, let's say 5 milliliters per hour, but instead of that, I know, okay, if I have 5 milliliters per hour, then in an hour I will need to have 50 0.1 milliliter doses, which means I will need to have one dose per 72 seconds or something like that. And each time there is this 0.1 milliliter dose to the vein. And that was based on CAT Prism PCA pump documentation. they did it in this way. Because the other way was to, of course, yeah, the constant infusion. But then, for example, there will be an issue with monitoring the volume dose in last hour. Because, okay, you had this speed, then you change this speed, so, okay, you need to make this all calculations. But when you have just 0.1 milliliter doses, you just make a sum of it. And then verification is easier. You don't agree?
I don't agree, but then continue.
Okay, I'll be interested in different solutions, but
No, I don't agree that your solution is any more simpler than the solution of calculating when you change the rate. In terms of specifying the rates in different units,
well, but
summation versus probably a
okay.
multiplication.
Okay, but you know, here in addition to basal rate, you have also patient bolus. And there was an issue, for example, okay, so when patient push the button, then what we are doing? We are just changing the rate to patient flow rate, or we are summing the basal flow rate plus patient rate. And okay, so how it's supposed to be done? What if clinician then requests the bolus, right? Okay.
So you see, there's a difference between the discrepancy in our misinterpretation of the specification versus how you implement it. So the earlier, my understanding was you were sort of alluding to whether can you use summation versus maybe a different sort of factoring of the given dosage. And now you're sort of alluding to the misinterpretation of the specification. Two different problems.
Well,
as
but
in, do you give it above, or is this bolus requested by the patient versus the doctor? And so how you sort of differentiate that? That's a different problem. Rather than different problem from if I've been giving a certain set of dosage, now do I calculate the next set of dosage based on what he has consumed for the last half an hour or 30 minutes?
okay. Let's discuss it after the end because yeah, my time is okay. Yeah.
Good tactic.
Yeah, because yeah, I'll be really happy to hear because you know there are different opportunities, and I was struggling again. What is better? But this problem. Then okay, then I found this the simplest solution. Anyway, yeah. So now I will switch here so to show the demo how it works. So here is the Linux operating system, and you know this is the actual pump. This is Vivo board. Here is a drug vial. This is a patient vein, and this is a clinician console.
Right, big way.
Well, this is a prototype. So yeah. So first thing is to enter prescription. So I will, let's say, specify the basal flow rate for 10 milliliters per hour. Then patient bolus will be 1 milliliter, and max drug per hour. For demonstration purposes, I will put 2 to get over infusion and show how it pump switch to TDO rate. And minimum time between patient bolus, let's say 5 minutes. Okay, and now just to confirm, display the prescription. Okay, it's correct. And so current state is stopped. So now I will run the pump, and the device started working. And first 0.1 milliliter dose is on the way. So in 10 milliliters per hour, we'll need to have 100 these doses in an hour. So that means we'll have 1 dose every 40 seconds or something like that. But we can do the patient bolus. So let's issue patient bolus, and now we can see that pump is in the bolus mode. And also in implementation and in the requirements, it is specified that the patient bolus has higher priority than clinician bolus. So for example, if now I would like to make a clinician bolus, let's say 2 minutes, then I'm still in the mode of patient bolus. And clinician bolus is waiting until the patient bolus will end. And I think it makes sense because when patient issue the bolus, and then clinician bolus will interrupt it, then the patient bolus has to be paused and finish after. But then when patient would like to have an extra request, then it will have to make it later, right? Because the balls probably will end up later. So in order to allow the patient to maintain the, for example, in this case, 12 requests per hour, patient balls has a higher priority. And so for now, 0.7 milliliter was infused so far, and there is still patient balls. So the pump will switch to clinician balls probably after 4 more doses, so the pump has 2 main threads. Maybe I can show the best part. So this is the code of the pump. It's created in Spark Ada, as I mentioned. So and there are 2 main threads: rate controller and max drag per hour watcher. And rate controller is controlling the rate in which the pump works, and max drag per hour watcher is another thread which just monitors whether overinfusion happens or not. And in case of overinfusion, it changes the mode to KVO rate, and then rate controller maintains KVO rate. Let's maybe go back to slides. I already switched the so it takes a time because also this prototype device it's not very powerful. So yeah, that's the almost the highest speed I could get, and also there's hardware limitations that I can only use 5 volts for this. In addition to the prototype, I also created simplified ADL models, and this ADL models has, of course, types and the operation module. And here is this simple operation module. What is nice, we can see it graphically. Yeah, so there are like the different ports, and they are in one package. And the way how it was translated in Spark Ada is specified in my thesis in translation schemes. I won't be showing that, but I can show the translation. So this is this code which was like directly translated. So for example, the first 4 procedures is translation of event port, because there is some event like start button press. There's here is data port when you specified the duration of clinician bolus, because during clinician bolus you infuse the same amount of drug as in patient bolus, but you specify the time in which you infuse this. And also here are the different threads, and here there's this generated code, and you can start doing verification. So when I run examiner, here I will get a first error that something is wrong with task, and what is wrong is that task is actually not using any. It's not using anything. There is nothing in there, so it's obviously something wrong. I need to start implementing it, and that's the first indication from the developer. And here's the partially implemented. So here I specified that the tags will use at least the time library, and when I verified this, I only got the warning that any VC was not generated, because in order to generate VC, the verification has to be performed in the body. So here is the body, and when I run examiner on it, I got different flow errors. These flow errors are saying that, for example, the first one, okay, so in this thread you declare that you will use this variable, but you are not using it. So in order to fix it, the developer starts doing implementation, and during implementation he will eventually get rid of all of these errors, and then the syntax will be correct, then you can perform the actual verification. Yeah, so I think stop. Yeah, and now we are in KVO rate, which is 1 milliliter per hour, which is 10 doses per 10 0.1 milliliter doses per hour. So probably after 5 or 6 minutes, you will hear the pump running again.
So is this ADA code?
Yeah, this is ADA. This is Spark ADA. I mean, the Spark is,
Right.
for example, this contract.
Right.
But yeah, this is ADA.
So did you write everything in ADL and then translate automatically to ADA, or you wrote some to
I didn't create automatic translator yet. I just manually translated.
But you did first write the ADL model.
I was, the ADL models, the original ones, was created by Brian Larson, and then I created this, simplified version of models based on his models, and then I took these models and translate based on the translation schemas. Like for example, here is like example translation of in data port. So when in ADL you have in data port, and in Spark ADA in the package specification you have procedure, and in body you have implementation. And in this case the generated will be empty procedure because how this port will work, in architecture level we don't really know as long as we don't have any connection. So will have to be specified by developer, or we'll have to have specified connection. But yeah, so this is like simple translations.
So does ADL have a way of specifying time?
Yes, like for example in thread you can add property and specify the thread period. And then actually in my translation this is not handled, this is sort of future work, but for example this might be useful because then every thread will work in some specified period.
But is that really, ADL knows this means time, or is subject to interpretation? So in some sense, is ADL time agnostic, or it has a built-in notion of time in the language?
I don't really understand the question.
So is there a fixed semantics for ADL, or it's just a syntax people can define as semantics based on the problem domains? Like in your domain, you probably need some notion of time.
Yes.
As part of your specification.
Yes.
So
in case of ADL, I think because it's architectural language,
right.
so I think it's only like sort of property, and then depending on the tools,
right.
you can interpret it for different ways.
Okay, so it's more. It does not have a fixed semantics.
Yes,
just
that I believe how it works. Yeah, because ADL is just description language. It's not like real programming language like Spark ADA. So the time can be used only by tools, and how tools interpret them probably depends on different tools.
So the ADL model was developed by Brian Larson.
Yes.
So he essentially had sort of, he has his own mapping from the syntax to what it actually means, but someone else could have another different model that does the same thing for the same part. Right?
You mean the tool?
No, the ADL model, right? So it is the case that if I have certain requirements for this device,
yes,
it's just depends on who designed the model. It may look completely different, or they all look similar.
Okay, I see what you're saying. So no, I think based on the ADL standard,
right.
There you have this notion of time, and then you can use it, and so all people will use the same models. But then then how tools interpret this,
right.
It depends.
So the standard is more like a convention, like people use that.
I would say that.
Okay.
Yeah, because there is no actual compiler for ADL or such a thing, right?
There's standard property sets for configuring the underlying real-time operating system. So things like period and for the threads and deadline and all that sort of thing.
Yeah, and unfortunately, like this properties were not captured here. It's future work because it's more advanced feature. Okay. So at the end, I performed this verification, and the verification scenario was, as mentioned before. So first, the examiner generates the verification conditions, then Spark Simp run Simplifier, Zombie Scope, and Victor, because this is a tool which runs those three which tries to discharge those undischarged VCs, and then POGs generate the report. And the strategy was as follows: that until this, when there are some undischarged VCs, was to try to fix the issues with Bakar-Chiesa. And then after the issues are fixed, then toolchain reruns, and hopefully some issues are fixed. But at least Bakar-Chiesa can show us better idea why some problem occurred. So created. Looks like this. This is the sort of module to monitoring the max allowed drag per hour. And there are three main procedures. The read dose, just read the dose. Increase dose means that, okay, I requested this 0.1 milliliter dose and add this to the last hour infused amount. And move dose is just moving the window. So every second when time is ticking, I am sort of moving the array and ignoring the previous values. And when you run Spark tools on this, okay, examiner was run, and now there was this internal representation generated. And I will run also the Spark simp, and here you can see that the zombie scope and Victor was run, and simplifier. And at the end, I am creating POGs report. And here is like a small summary of there's 4 undischarged VCs, and this is this report. And it looks okay, but if you want to, like, for example, find out, okay, here's some undischarged verification condition procedure, move those. So what do you need to do? You need to go, okay, so let's, where is this? It's here.
You have some example contract for this device, but you do have pre and post for those.
Yes,
devices.
yes.
You
So
have some of those examples that you can see what type of properties you want to prove.
okay.
Right. So can you just go through one of them?
Yeah. So for example, we have procedure remove those, and there is a post condition, right, which says that always the last element of array is 0 because the window moved, and there are like sort of 2 cases. And the first case is that the first element is equal to 0, and then after the procedure runs, the total sum of elements has to be the same. But when first element was greater than 0, then the total sum of elements will be lower than it was before. So, and like for example, here, the move those, as I said, you need to go to VCG file, open it with, and you need to even specify that it's text file. So let's use Sublime Text, and and this is how it looks. So like, good luck with analyzing this because it's not very friendly. But what you can do, you can use Bakar-Chiesa, and then when you for example run, let's run this on maybe entire package.
Do you also have a contract with time? Because you do have every.
No. That's the issue. That's the issue, how to do this, and especially like for example, when you use a Ravenscar multitasking profile for Spark data, you cannot use pre and post conditions in threads and for protected objects. So
how is time enforced on this? You have a timer, you have an interrupt, or also how do you know when to issue the next injection?
So here is, for example, the rate controller, and there is this operate switch. Right. Once it's set to true, it starts running, and then it's just constantly running. And for example, when we are in, let's say, basal rate, right? Here I'm checking whether because 1.0.1 was dosed. Okay, so then I need to wait some amount of time for next dose, and here I am just checking. Okay, this time passed. Should I issue another dose or just
hold the system for time?
Yes.
That's contracts
have a notion of time included.
And that has not been incorporated in.
Yeah,
Okay.
yeah, it was not because yeah. So here is example TSM report. Maybe let's do it like that. By the way, this plugin was created by me. So here is this move those contract, for example, and
Which is not
here.
part of his official master's work.
But it's useful for his
It's
master,
some,
as you can see.
Yeah. So and here you have two possible paths, right? And Kiesan can easily tell you why. First path is when the first element is 1, and then after procedure is run, it's 0. So that means it was ignored. But in second case, the first element is 0, and another is also 0, and the sum of elements is the same like it was before.
How long is it?
Excuse me?
How long is each of those columns?
Oh, 60 elements. Actually, in the working version, I have 3600 because for every second in an hour. But here, for verification purposes, because the time space grows very fast. Actually, it's very good that it works for 60 elements because it's still a lot. So, like for example, there is an example of one program which is sort of implementation of list, and I think we are verifying it with 3 or 4 elements. And
Which one?
RI set,
Oh, okay.
yeah,
Probably verified for
8. Yeah. So you see, here is
But
60.
but the complexity is different. So you cannot
Yes.
compare just based on the
Yeah,
size,
sure.
but the complexity of the algorithm.
Yeah, I mean the issue with verification
Yeah,
is
it'd be
the time. I mean the possible states. How many possible states you have? Because more complex system, more things can happen, and
Right. So anyway, you could try with 60, and then when you fix the issue, then you can try it back to 600.
yeah, that's a like strategy here. Actually, I was starting with 6 elements, and then I increased it to 60, and then you can assume that the same will happen for 3600, or you can run it through the night, for example.
But when do I stop?
Oh well, I mean in this implementation I am using 3600, so.
I mean, in general, when do I stop?
There is only 3600 the time unit, right? So you consider.
Yes, because here I have this type, which is defined that it can have only like 60 elements. And in implementation of real pump, I have 3600, right?
So it's type check.
Yes. So and especially what is nice in Spark that is definition of type ranges, and yeah, it's also used here. There's created drag volume type which doesn't have negative values because it's not needed.
You have to stop somewhere for emulate system.
Yeah. I understand, and I'm asking where.
Well, depends. Because
Right. In this case, you.